Hello, my name is Bojan, and it's my pleasure to present to you our project called DataScope. Its focus is on finding efficient ways to perform introspection of machine learning pipelines for debugging purposes. This work is a joint effort between my collaborators from both ETH Zurich and Microsoft. Our story begins with a developer who is working hard to train a machine learning model. This work involves building ML pipelines like the one we see here. This is an iterative process, and many times something just doesn't work as expected. The issue could be that the accuracy is simply very bad, or that the model's errors are biased, making the predictions unfair, or that the model failed to be robust against some adversarial attack. Whatever the case may be, our developer must now inspect the ML pipeline in an effort to pinpoint the source of the issue. One common way of looking at this is to measure how a specific element of the pipeline, for example, a specific data example, influences the final outcome that we care about. This is an active area of research with many proposed approaches. Some methods use influence functions as a measure of importance. Another line of work, which our own efforts are based upon, is about using the Shapley value, a concept from game theory, as a measure of importance. The challenge is, however, that most ML pipelines are not simply made up of training data being directly funneled into the model. In most practical settings, our workflow is made up of a relatively complex set of data preprocessing operators. In these settings, training the ML model is only one of the steps of a larger pipeline. Unfortunately, most existing work in this space focuses only on training data and not on the pipeline itself. The challenge is that it is tricky to compute a meaningful importance score while at the same time not having to rerun the entire pipeline many times. We propose DataScope as a solution to this challenge. Its method consists of the following two steps. First, we track the provenance of individual tuples of training data as they move through our pipeline. We can think of it as a way to know for each data point which pipeline operators played a role in producing it. Second, we extend the machine learning algorithm to take advantage of this provenance information in order to efficiently compute the importance of individual pipeline elements. In the remainder of this presentation, I will cover the following three topics. First, we will take a look at how we measure importance and what interface do we provide to the user. Second, we will do a quick overview of our method and see in which cases we can provide some computationally efficient results. And third, we will talk about the applicability of our method to real-world pipelines, and we will go over some experimental results. Our system works with machine learning pipelines which might look like the one we have here. Our task is to determine the importance of some specific pipeline operator relative to some set of operators. Importance is always defined with respect to some specific metric which is computed using some validation dataset. The good news is that our entire system can be subsumed in a single query which takes in several parameters. They are the target pipeline operator, the structure of the pipeline itself, the set of operators relative to which our importance is expressed, the validation data, and the metric. Now, the next question is, how does one even define the notion of importance? Our viewpoint is that the importance of a unit is proportional to its contribution to a group of units. For example, if we have a group of 3 units and we want to know what is the importance of some target unit, the answer should depend on how well that group performs without the target unit. This involves computing the utility of the group with the target unit present and comparing with the utility with the target unit absent. However, the contribution of an element might differ when we look at the whole group as opposed to looking at some subgroup. This leads us to the question, which subgroup should we look at? And the answer is, we need to look at all of them. It turns out that there already exists an established method in game theory for computing the value of a unit with respect to a group that has many useful properties. It's called the Shapley value. The challenge is that it is hard to compute as it involves a sum over exponentially many subsets of units. Our goal here is to make this value computable at scale. In an effort to apply the theoretical notion of Shapley value in practice, we start off by reconstructing the formula a little bit. Instead of summing over subsets, we are now summing over binary vectors. Our utility is now the accuracy of the k-nearest neighbor model. We've chosen it due to its simplicity, which makes it much easier to analyze. The binary vectors now determine the candidate dataset instance that gets passed into our model for training. The problem here is that the number of these candidate datasets is huge, so we need a more space-efficient representation. One approach is to annotate each tuple in the dataset with a logical formula that controls if it is present in the dataset or not. The question remains, how does one decide which formula should be used to annotate each individual tuple? One possible answer comes from database theory in the form of provenance semi-rings. This gives us a principled way to think about tuple annotations and how they should be transformed as a result of applying pipeline operators. This offers us a useful abstraction to model arbitrary pipelines. However, using this abstraction, it becomes clear that even for the simple K&N model, computing the Shapley value remains computationally hard for arbitrary pipelines. One question that we focused on is, can we find some settings in which this problem can be made tractable? To answer this question, we looked at many real-world pipelines and tried to see what kinds of operators they have. We concluded that a large number of those operators can fit into one of the two categories: map operators and fork operators. Map operators are those that for each single input tuple produce at most one transformed output tuple. On the other hand, we have fork operators. They map each input tuple to a set of transformed output tuples. We can see how, in both cases, the polynomials in our annotations are actually very simple. It turns out that, luckily, for pipelines that contain only these two categories of operators, our algorithm for computing the Shapley value can be made tractable. Specifically, if the size of the k-neighborhood of the K&N model equals to 1, which is the simplest case, our algorithm runs as fast as it takes to sort all the tuples in the dataset. And when k is greater than 1, we show that our method can also run in polynomial time. Now, after we've seen that representing operators as either map or fork leads to efficient algorithms, we can take a look at how this abstraction fares in practice. Specifically, we can look at our example pipeline and try to see which operators can fit into our map fork viewpoint. Since data subsets are units that generate a multitude of tuples, this makes them fork operators. The missing value filter operates on single tuples, which makes it a map operation. Data augmentation is a typical fork operator, as every input tuple is replaced by a set of transformed tuples. Looking at the min-max scaler gives us a bit of a headache. The problem is that even though each tuple gets scaled independently, to compute the scaling, we first need to compute the minimum and maximum values, which depend on the entire dataset. Luckily, we can come up with an approximate solution. It relies on pre-computing the minimum and maximum values and then treating them as constants. Conditioned on those constants, our operators can now be treated as regular map and fork operators. Okay, so we saw that it is possible to represent a realistic pipeline with map and fork operators. But how many real pipelines are we actually able to fit into this view? To go beyond our simple example, we looked at a large pool of about 500,000 machine learning pipelines that we obtained through our collaboration with Microsoft. These pipelines were generated by internal users of the ML.NET framework. As we can see in this histogram, the vast majority of pipelines are either strictly map fork or they are conditional map fork, meaning that they can be represented using our approximation scheme. We perform an extensive experimental study of our method. Here, as an illustrative example, we show the results of one experiment. In the scenario we show here, we deliberately corrupt 50% of our training data examples by flipping their labels. We then compute the importance of each data example. Then we take a fraction of the training data examples with the most significant importance score and we repair their labels. Finally, we check what is the accuracy of our model after repairing a given fraction of data examples. We also check how many of the corrupted data examples we were able to catch with our importance measure. We compare our method, K&N Shapley, with a solid baseline, TMC Shapley, which is an efficient version of the standard Monte Carlo method. As we can see, it is able to match its performance while at the same time being even up to 1,000 times faster based on our measurements. Finally, we can notice that the performance of pipelines with condition map fork operators is very similar to pipelines without conditioning. This implies that our approximation scheme can indeed be effective. To summarize the main contributions of our work, we show how we can view pipeline operators as being either map or fork operators. Using this abstraction, we show that our method to compute the importance can be made computationally tractable. We then show how many of the operators that are not strictly map or fork can be approximated by conditioning on some pre-computed information. Finally, we perform an empirical study that demonstrates the usefulness of our approach for various pipelines in various scenarios. I would like to thank you for your attention, and I would also like to thank all my awesome collaborators, my colleague David, our Microsoft collaborators Matteo and Wental, as well as our advisor Ce. Please reach out to us in case you find this topic interesting and would like to discuss. Thank you.